is Daniel Connolly, and I am presenting a presentation for a paper I got accepted in ICBC titled Have I Been Exploited? A Registry of Vulnerable Ethereum Smart Contracts. And this is me, and then this is also my advisor and professor who co-wrote this paper with me. So in this presentation, I won't go over some basic things like what are smart contracts or what is a blockchain, because I just assume that people know about this sort of thing. But I would like to explain some certain details about Ethereum and some of the specifics to Ethereum blockchains and some of the history that kind of spurred on this research and proved to me how the importance of why this digital registry of smart contracts that are vulnerable is a good idea. So to start with the history, there are two kind of big historical losses that I'd like to focus on as the impetus that drove my idea. So I'm sure there might be more recent examples, but these are ones that I referenced at the time of writing this paper. So firstly, the DAO. This is a smart contract that was launched in April 2016. It raised a whole lot of money, $150 million in one single address. In retrospect, that was a really bad idea because a vulnerability can be exploited, which I'll talk about a little later. What ended up happening was there was a vulnerability, and it was called a reentrancy bug, and this got exploited, and someone drained $60 million from the contract. It wasn't so bad. Kind of a theme of Ethereum is that there are some losses, but some big ones were able to be rolled back or avoided due to catching the bugs early. So in this case, this contract was reset essentially, and the whole blockchain was reset, so the damages didn't go through. However, as I said, there are some other examples of losses, and the people were not so lucky. So secondly, the more recent example is a Fair1 contract. This was an almost loss, as I call it, because even though there was $10.5 million of ETH in there, it was taken out by, assumably, the people that owned it. There's really no way to tell, but we assume that is the case, as only the contract owner could have taken the money out, and I don't think there was any record that they did that. So as I said, I was going to talk about this a little later. So there's this vulnerability aspect, and what I'm focusing on is the vulnerability piece, putting smart contracts into this digital registry, the ones that are vulnerable. And so we kind of think, it's okay. It's not a horrible thing. What is horrible is when it gets exploited. That's a little more deadly. But if just a one sentence, what is a vulnerability? It's a weakness in software systems. And so, for example, you could have an integer overflow. Some variable could overflow, but the variable may not even be used, or it may not be used for anything important. So the program may behave not as you wish, but there's no money or Ethereum that gets lost in that process. So an exploit, on the other hand, is a little different. So exploits leverage vulnerabilities. So same example, except with underflow. If you had an underflow from some variable, maybe your bank account goes from $2 to the maximum of an int, and that's obviously a worse situation for the bank, at least. So kind of to carry on with more examples of some vulnerabilities and some exploits, some easy ones so people can understand how it works in Ethereum. So and this is one major, really easy exploit to understand. It's called unprotected self-destruct. People have different names for it, but this is one we can go with here. So this vulnerability and this exploit, essentially, you have is made up of a contract where you have the ability to destroy the contract, and that's something that's kind of unique to Ethereum. You can destroy the contract, and whoever destroys that contract can receive back all the Ethereum in that contract. So here we have an example of some code where there's a self-destruct function, and it sends it all the money in to this address. The person that's message.sender, the person that's calling this function at this contract, they can receive all the money. This is an unprotected self-destruct. If you wanted to protect the self-destruct function, the close function, then you would check, is the sender the same as the owner of this contract? So then only the owner of the contract can actually destroy this contract and receive the funds. So as a part of my research, I analyzed a portion of the blockchain of Ethereum, and this is just an example, again, of that self-destruct program or that function, but in a real example. So this contract had $25 worth of Ethereum. It actually went up because Ethereum's price skyrocketed since then. However, luckily or fortunately, the owner did finally destroy this contract, and that was good because I could have taken money out of it, for example. So this contract, this is the output that I had that described the issue from a tool I was using called mithril. So the transaction sequence goes like this. So first you call the set owner, and that makes you the owner. You're the message.sender. And then the second transaction you make is to the kill function with this data, which essentially makes you or checks if you're the owner, and then it destructs the contract if you are indeed the owner. And if you called this function, you became the owner of this contract, and then you are able to take out all that money, which is probably not what the owner of this contract had intended, and is a case example of why a digital registry would be useful, so that people could be able to check their own contracts and see, is my contract safe? Am I going to lose the money I put into this? As an example. And yeah, you can see the transaction that I did, but it wasn't on that address. It was on a contract that I copied the source code to, that had the same source code. So again, my idea is a digital registry. I'm going to talk about why this isn't a good idea beyond what I've already explained. I would like to start with the state of the art. There is no insurance for Ethereum smart contracts, by default at least. This is kind of in opposition to what currently exists, like a Consumer Reports type of business where they tell you if a product is good to use or bad to use, or a VirusTotal product in the antivirus malware domain. They scan a bunch of files with a bunch of viruses, engines, or malware engines, and give you results back to tell you, is this file or these files safe? And then furthermore, the Better Business Bureau is another example where the Better Business Bureau will tell you what businesses are safe or what businesses are not safe. So the same idea can be put onto Ethereum. In a recent study that showed why this is a good idea came from a Trail of Bits research study, and they found that 50% of general smart contract flaws and 78% of the most important flaws, think unprotected self-destruct, can be discovered with static and dynamic analysis tools. Symbolic analysis execution is an example of such a tool, and you can detect a lot of vulnerabilities with that tool. This is the tool that I used in creating this digital registry prototype. And as I did in my project, you can parse this data and put it into a database so that other people can make use of that information. So furthermore, If someone is trying to do this on their own, it's going to take a lot of effort as opposed to a single centralized registry or even a decentralized registry that multiple people are contributing to. So here's some examples of why it might be a better idea to create a single registry. So for one, tools are cumbersome to use. If you're not a CS major or if you're not really into the space, it's kind of hard to learn, and some of these tools are very specific in what they want you to do, and it's not just clicking an exe file and having it be installed and run really quickly and easily. Secondly, tools aren't really advertised to people, so sometimes a researcher will come up with this really cool tool, but not everyone really knows about it, or just the same as a company might do the same. Some of these tools as well are expensive, so you may not be able to buy them, but if a registry were able to use that tool, buy that tool, they may, depending on the license from the company, may be able to use that tool on a massive scale and share that data with multiple users. Another point that owners and users of vulnerable contracts can't really be contacted because the blockchain is anonymous. Unless they self-identify themselves, everything's anonymous on the blockchain. And these results that people are trying or would benefit from receiving takes a lot of time, a lot of electricity, and a lot of money. I spent a very long time trying to get results, and some of these contracts took an hour or more, and I had to cut it off at an hour to get results back. Furthermore, I spun up many machines, which took a lot of electricity, and I blew through $5,000 worth of cloud credits to receive partial results. So we really can't, I think, expect average users to be doing this because they don't have that many resources. Another idea I think that is good for a digital registry and kind of makes sense why a digital registry should exist is that we really need a rating system for some of these contracts. Just giving people vulnerabilities isn't helpful enough to them because they're not able to decide if that's a reason that they should step away from the contract or if they should continue on using that contract. We need to give them more insight than that, just like the other institutions like the Better Business Bureau, Consumer Reports, etc. And I think we should use multiple engines as a base for that rating system, as not all engines are perfect. So this would hopefully statistically cover some better ground when it comes to determining if a contract is safe to use or not. Even more so, I think some of these systems, these engines can be rated. So as I said, not every engine is perfect. Some of them have bugs themselves, so we can rate these engines as well. And another thing that was very helpful to users is unifying the names that we call these vulnerabilities. So depending on what engine you go to, sometimes a self-destruct can be called an accessible self-destruct or an unprotected self-destruct, and users are probably confused with all these different naming conventions, and a digital registry would be good at unifying those vulnerability names. I could go on, this last slide I promise, but I could go on about this because there are a lot of reasons to use this sort of system for exposing vulnerable contracts. Another one is that users can search a contract before using it. Vulnerable contracts are less likely to fill up with Ethereum and cause a giant exploit later on. Users can remove their funds from insecure contracts. Developers can be made more aware of the problems in their contracts. They can redeploy new contracts and alert their users of that contract to follow or invest or use the new contract. And I think generally just having a digital registry provides user confidence that, hey, these things are safe. You won't lose your money if you put money into this. As I said, there are similar works being done in other domains, such as Consumer Reports, VirusTotal, Better Business Bureau. The Have I Been Pwned website, if anyone's familiar with that, you can enter in your email address and you can find out if your email address is part of a leak or is on the dark web. And then similarly in the Ethereum chain or domain, there is actually a recent example where people have kind of, I think, adopted my idea because I released this, it was like 7 months before this website came out as an idea, and I think it was January this website came out of this year, and they've decided that they want to kind of do this digital registry, but they haven't really developed it as of yet. And there are probably other decentralized listings of different ideas that people are doing right now, but it's hard to really find out because things are decentralized, even though there are some resources that are centralized. I skipped over this, but there's actually an idea similar to mine that's been around for a while called Contract Library, and they use their own software called the DAUB to run analysis on the blockchain. Currently, it's up to date. Every new contract they scan with their tool, which is ideally what I would like mine to be, but a little more fleshed out. So using other engines and other having a rating system, that sort of thing. But this is a good, I think, example of what I would like mine to be like. So, just kind of a brief walkthrough, if in case people aren't familiar with symbolic execution. Essentially, you have a program, such as this very simple program. There are 2 states to get to. There may be n amount of states to get to in a regular or a larger program on Ethereum. But essentially, a symbolic execution engine tells you, how do I get to this state? Good job. And how do I get to this state? Try again. And in Ethereum, you might replace good job with send all ETH to the caller's address, or, just like close the program type thing. And so the idea is of using a symbolic execution engine for this Ethereum program is you want to find out, is it possible that anyone can get to some exploit? So if this line was this right here, that would be an exploit. If anyone could get into this area just by typing in Hunter2, then that's a big problem for people that are trying to write secure smart contracts. And just a graphical form, a little bit more on symbolic execution. Here's a little graphic that describes the process that symbolic execution would take on a smart contract. So you have your smart contract. You create an abstract syntax tree of all the different states that you can get to, and then you create a control flow graph that you can traverse down selected paths to try to find a potential risk, such as the unprotected self-destruct. And then if you find one, you can output the risks, the locations, and the inputs on how to get to that state. In Mithril, the tool I was using, they discover 16 vulnerabilities. They disassemble the bytecode, use Laser, which is a symbolic VM that they wrote that can run the EVM instructions in that control flow graph to find the vulnerable states. For example, something like that, the purple highlighted state right there. This is pretty important, and you do need to find a vulnerability in order to put that into a digital registry. But this is a complex process. This is a computationally expensive process. I just feel like it's important to note. Again, another reason why a digital registry would be useful. And then another thing that Mithril does really well is that they are able to prove a path is possible to get to using this thing called a Z3 automatic theorem prover, which was written by Microsoft, and I believe it's still maintained by Microsoft. And that is useful later on for some future work that I have in mind, which you will see on the future work slide. So this isn't meant for me to go over in depth, but you can just look at the different with different vulnerabilities on the left here, and then the descriptions of the vulnerabilities on the right. You can just pause the video since this is a virtual conference. And just to give you an idea of what kind of vulnerabilities Mithril is able to catch. So I started out my process of building this registry using the Geth node to discover all the contract addresses on the Ethereum blockchain at the time of doing this research. After that, I spun up multiple VMs in the Google Cloud Platform service, and I ran a Python program that I had written that spawns approximately 10 threads that spawned Docker containers in each of those threads, where each container was given a contract address to run the image of Mithril with. So this is to overcome a limitation of Mithril at the time of this writing. There's more straightforward ways to do things, but I had to do it through this way, unfortunately. And I put out the output of the Python program into different bins, as I call it, or different text files, really, depending on the output of the program. So if there was exceptions in that program, I would put it into an exceptions txt file. If there were errors, I would put the errors into that file. And these two files helped me to debug some of my program, but also helped me to send bug reports to Mithril and just verify some of my results, and then also rerun those results that failed. And after Mithril would release a new fix for that new patch. And then lastly, probably the most important text file that I was saved was the Mithril output file, and that was telling me what contracts were vulnerable, and that I parsed that into and then inserted that as a row in a table in a database, and that is basically what made up my digital registry contract system that I've created here. So this is just a high-level view, just graphical, if people are better with graphics than words, and just says the same thing I said on the previous slide. So my results, it took approximately 50 days of, I shouldn't say really compute time, I should say, days. The compute time, if you're going to count gigahertz, is probably going to be a lot more than that. I believe, this was number, so it was 3 million contracts from the 0 to 9 millionth block that I discovered. But it's important to note I only achieved a partial analysis through this 0 to 8.4 millionth block. And out of this range, which I didn't analyze all of that, I found approximately 800,000 contracts had vulnerabilities in them. So this sounds like a lot, and I think some of these results, just I need to pause here and say that a lot of these results will sound like, oh my gosh, Ethereum is so insecure and horrible, but a lot of these vulnerabilities are actually like not a big deal. They're not able to be exploited. That's the important thing to remember. So approximately 26% of these Ethereum contracts have vulnerabilities. If you do 800,000 divided by 3 million times 100, and then also it's important to note that not all of these contracts were live. So some of them were dead. They had so the ratio actually would be higher of Ethereum contracts that have vulnerabilities, because that 3 million number includes contracts that have been self-destructed. And then it's also important to note that the number would be higher because there were time constraints, that I was only able to scan for an hour because I was trying to finish the entire 9 million blocks in the time that I had. But even then, that still wasn't enough. And then, furthermore, I just stuck with Mithril's default transaction amount call, which is 2. If you do 3, 4, 5, it becomes exponential, the amount of state space that you have to search, and that makes the time that you would have to execute even longer. And I was just trying to stick to an hour, so I decided to leave the default. But it would be interesting if other people would increase that default to a higher amount, or me if I have the time later to further this research. So approximately 1.2 million vulnerabilities were found within those 800,000 contracts, meaning some contracts had more than one vulnerability. I'm not double counting those vulnerabilities, by the way, so there could be a contract with multiple functions, and all those functions have the same vulnerabilities, but that's not included in this 1 million number. Furthermore, if you want to look at the money, if you just said, oh, well, if it's vulnerable, then it may be exploitable, and this is the amount we have at risk for the entire chain. Even though I didn't get through the entire chain, you could say at least 2.5 million Ethereum is at risk. And this is before Ethereum's price has exploded on the stock market and just in general. It was $430 million that was at risk. But again, this is not very serious, considering some of these exploits are not serious, or vulnerabilities are not serious and not able to be exploited. Okay, so I also compiled a number of graphs to show what things looked like in a little more detail. So these are the contract addresses per block, per millionth block. As you can see, Ethereum has grown in popularity over time. Around this time, the 4 to 5 millionth block, the Ropsten network came about. So that's, I think, why some of these contracts have lowered. People aren't using the mainnet as a test net anymore, so that's a good thing. So furthermore, these are the vulnerabilities that I found, the types of vulnerabilities I found in these contracts. So 646,000 about vulnerabilities were this exception state vulnerability. This is actually not a serious vulnerability. So that's kind of what I was saying, that 26% vulnerable number is, or percentage, is not very concerning, because all these vulnerabilities can't be exploited. Essentially, just the contract fails and everything gets reverted, but every transaction gets reverted. But you're not able to take money out of a contract just based off of that. Some of these other vulnerabilities are a little more concerning, like the unprotected ether withdrawal would be a little more concerning, and so that could be used as an exploit. But again, even still, some of these vulnerabilities aren't able to be exploited, and some engines do have bugs. So another graph here, another histogram. So there are a variety of vulnerabilities per millionth block. As I said, this is the time where the Ropsten network came about, so I think a lot of people were using this as a test network, and they were deploying things and then finding out that they were vulnerable later, and they just left them on the blockchain, I think, and maybe they didn't even program a self-destruct into the contract. So potentially they may have not had any other option, and that's why we see a lot of vulnerabilities in these earlier blocks. And as I was saying before, you can have a viewpoint that anything that's vulnerable is at risk of losing money. So again, same story here. The middle is around where the Ropsten network came about, so sometimes I think there are some bugs here that people got caught in, and then their money was stuck there and they couldn't do anything about it. But Ethereum was cheap at the time, so people probably didn't care that much either. So this is the main results of my research here, as in the front end piece of it. It's a website I developed. I'm sorry I didn't update this. You can say HTTPS now. It has a security certificate. But it's a registry of the results in this research. And as you can see, you just simply type in a contract address, and if we have it in our database, we will list the number of exceptions that Mithril is able to find, and then we'll also list whether it was found to be vulnerable in that's sort of in the category of exceptions. So this contract is not very vulnerable. You can scroll down even more if you want to type this address into the computer and see more vulnerabilities. I believe it only had 2, but exception state was the main one. And again, that's a really weak vulnerability. But this is just a proof of concept, so I would really like to further this idea, but this is what it looks like right now. So I think there's some room for discussion here as well. A number of bugs in Mithril kind of cast doubt on some of results of some of these engines, perhaps. So the self-destruct vulnerability, for example, the exploit, it was not really reliable all the time. There was at least 2 or 3 bugs I found just by looking at the bytecode and decompiling it that this was not giving accurate results. This was good to tell them about, and they were really eager to fix it, and that was really good. But we should really be rating these engines as well. That's kind of the main point, I think. And then there are some ethical concerns. Some people may not like the idea that you're releasing these contracts and saying, hey, here's a vulnerability, because anyone theoretically could attempt to exploit that contract. But I think that since there is this contractlibrary.com by 𝒂𝒂𝒄𝒕 that already exposes these vulnerabilities in contracts, and there hasn't been any major upset in the system, I think this is a safe idea. Furthermore, as I said before, by exposing these things early, you're preventing a fill-up of these contracts to where they're just exploding with Ethereum, and then someone just cashes out all of these contracts because they finally found a bug, and millions of people lose their money. So it's kind of earlier is better than later to find out these vulnerabilities. And I think just, again, I didn't get through all these contracts. There's a lot more analysis that can be done, a lot more engines that can be put into this engine or this idea, and a lot more upgrades and features which can be done. But generally, I just want to reiterate that this blockchain idea, this Ethereum blockchain idea, it's really safe. It's increasing in popularity. Here's some news article type things down here that explain how quickly these things have been exploding, and 1.3 million transactions occurred in 24 hours on January 4th, which was a record for Ethereum at the time. And it might even be more than that, because currently the stock price or the dollar price for Ethereum is above $300 right now. And there was an article recently that said that the exchange on Ethereum, the amount of money that's being exchanged, is higher than Bitcoin right now. So I really think that Ethereum is kind of the blockchain of the future. So I would like to further my work by finishing the analysis, including other engines. These are some of the engines that I would like to include. And then also automating a lot of this. I think earlier on I didn't feel safe in automating it, but now I do, because I feel like I have more of a handle on this sort of thing. And then also rating these engines, rating these contracts, using the engine's ideas of what is severe as a pivot point to come up with my own rating system, and then also running deeper transactional analysis on vulnerable contracts beyond that default level of 2 that Mithril provides. And then generally just updating the website. I think a lot of the aesthetics could change, and things could be more efficient, I believe. This is a more recent idea that I don't have in the paper, but I would like to collect the Z3 outputs from Mithril, which I actually have already done. But then I would like to sandbox these Z3 results and then use them in a sandbox environment to run the contract addresses transactions that would expose or exploit those contract addresses vulnerabilities. And there's 2 programs called Theo and Carl that both together, when combined, they can do this sort of thing if I modify their code a little bit. And then lastly, I would like to integrate kind of this work into a browser, and then possibly, like VirusTotal does, and then possibly generate useful data science type of things, like how many, kind of like I already did, like how many contracts per block, that sort of thing, into the website as well. And Aleph.io is a business example that has already done something like this. So in conclusion, this is a really good idea, I think. I think it'll be a growing idea as Ethereum gets even more popular. I do owe a lot of thanks to my advisor, Wusong Fang, for guiding me through this process. Really happy to be accepted into this conference. This is my first conference that I've been accepted into, and really honored just to be a part of this process and to submit this research into such a new field. I would also like to thank the NSF and the Google Faculty Research Grant that was awarded to me to continue this research, and then also the Ethereum Foundation for connecting me with the Telegram channel, ETH security community, where I was able to ask for resources and questions and just share my ideas. Thank you for watching.